Swayam Prabha. Digital India. Educated India.
So you see, what we are trying to do is we are trying to get to this very important theorem, which is the theorem of uh, classification of curves. Okay, and the simple statement is that curves are classified up to rigid isometries, okay, by their curvature and torsion functions. Okay, so this is the mathematics that's involved. So what I'm going to do first is, we have already made sense of what rigid isometries are. Okay, rigid motions are. We have realized that these are going to be these are just going to be isometries that are going to be orientation preserving, and that means you can break them down into a translation and an orientation preserving linear isometry. And the orientation preserving linear isometry is a member of the special orthogonal group. Okay, a general linear isometry is a member of the orthogonal group, and the orthogonal group has the members have determinant plus or minus 1, and those which have plus 1, determinant plus 1, they are called the members of the special orthogonal group, and they are the oriented isometries. Okay, orientation preserving isometries. Okay, so what we are going to do is we are going to start with the curve. Okay, we'll take it to be a unit speed curve, all right, and then move it by an isometry, oriented isometry. Okay, that is a rigid motion, and show that the new curve and the original curve have the same curvature and torsion functions. Okay, so we have to first show that, right? So that's what I'm going to do. So start, so beginning of the proof of the classification theorem, for space curves. Okay, so what you do is that start with gamma of s, a unit speed space curve, parametrized by increasing arc length, by increasing arc length s. Okay, and we will take this arc length varying in an upper interval AB on the real line. Okay, it's more natural to it's more natural to start with some point on the curve which has 0 arc length. Okay, and go up to a certain L, which is the length of the curve. Okay, and then you could have taken closed interval 0 to L. Okay, as the as the interval. But the point is that you also want to be able to move backwards and measure arc length on the other side of the curve. Okay, in the direction opposite to the orientation. So in general, I am just taking a I'm just taking an arc length function which is varying from A to B. That means I'm looking at all portions of the curve, okay, whose arc length is between A and B. Okay, so A is and of course when I write like this, you should see that A being A should be strictly less than B. Okay, if I am having increasing arc length. Okay, so and of course arc length I am taking it as positive. All right, so and the reason why I am taking a unit speed curve is because you see I want to make use of the Frenet-Serret relations. Okay, because the Frenet-Serret relations they give the dynamics of the curve. Okay, and to write down the Frenet-Serret relations, you have to use only unit speed parameterizations. Okay, and of course, if you take any regular curve, you can bring it to a unit speed parameterization, a reparameterization, by just taking increasing arc length. Okay, so we do this. Now what you do is that take this curve and then you apply a oriented isometry, apply a rigid motion to it, and then the claim is that the new curve will have the same curvature and torsion functions as the original curve. Okay, so we claim that if m is a rigid motion of R3, okay, then the curve M circle gamma, okay, which is gotten from gamma by applying M is will have the same curvature and torsion functions as gamma. Okay, so remember, you see, so you recall that you see this that is the Frenet-Serret frame for gamma of S. Okay, and what is that? So you see, you have the so-called T cap, okay, and I will put subscript gamma, and T cap gamma of S is just, this is the unit tangent vector. Okay, and what is it? The unit tangent vector is, the tangent vector is just gamma dot. Okay, and this is a unit vector because it's unit speed. So this is what T cap is, and of course, this dot means d by ds. Okay, it is derivative with respect to arc length. All right, then once you have this, then you have the so-called n hat gamma of S. Okay, this is the principal normal. Okay, and the principal normal is defined by the first Frenet-Serret relation, namely it is 1 by kappa of gamma of S into T cap gamma of S. Okay, so this is actually coming from the first Frenet-Serret equation, which is T cap dot sub gamma of S is equal to K gamma of S times n cap gamma of S. Okay, so if you recall, we had this, how do you write the Frenet-Serret relations? You write them as T cap gamma, n cap gamma, b cap gamma. Okay, these are the derivatives of the Frenet-Serret frame. The Frenet-Serret frame itself is simply T cap gamma, n cap gamma, and b cap gamma. Okay, and the dot is looking at the derivatives. Okay, and this is related by this Frenet-Serret matrix, which is it is a skew symmetric matrix involving the curvature and torsion. So I will have here K gamma of S. I'll have 0 0. I'll have minus K gamma of S 0, tau gamma of S 0, minus tau gamma of S 0. Okay, and these are the Frenet-Serret equations. These are the Frenet-Serret equations. Okay, and what are the, so the Frenet-Serret frame is T cap, n cap. So the n cap comes from the, if you calculate the first member, which is first row into first column. Okay, you will get T cap dot is K gamma times n cap. Okay, therefore n cap is just 1 by K gamma T cap. Okay, and mind you, to write this, it's very important that K gamma is non-zero. Okay, so you need the important thing that you see. Basically, you want to also bring in torsion. Mind you, torsion is defined only when the curvature is not 0. So I'll have to we assume the curvature of gamma is never vanishing. Okay, and usually the curvature in the space curve case, we take only the magnitude. Okay, we put a sign to the curvature only in the plane curve case and call it the sign curvature. In the space curve case, the curvature is always the magnitude of the curvature. Okay, and therefore it's always if it is never 0, it's always going to be a positive function. So never vanishing, hence positive. Okay, so you assume that, so that I can, this division by k gamma s here is justified, right? Then what is the next thing? The next thing is, once you have the tangent, unit tangent and the principal normal, which is the unit normal, then you have to get the third one in the Frenet-Serret frame, which is the binormal, the unit binormal. And the unit binormal is defined in such a way that it completes the orthogonal right-handed triad. So the third one will be just the cross product of the first and the second in that order. So b cap gamma of s will be this is the binormal. Okay, and this is going to be just t cap gamma of s cross n cap gamma of s. Okay, and of course then it is it is a computation that you get this matrix, okay, that we have already done. All right, now so this is the Frenet-Serret frame, and what I want to say is that so the picture is like this. I am here in R3. Okay, and and I have, this is my gamma of s. Okay, and I'm going to I'm applying a rigid motion m. Okay, m is, mind you, it is a map from Rn to Rn. It's a rigid motion. When you apply this rigid motion, what is going to happen is that you are going to get so you are going to get the new curve that is gotten by moving the original curve by this rigid motion. Essentially, you can think of the rigid motion as first a translation, okay, followed by a generalized rotation, and a generalized rotation which is oriented. Okay, so so basically, if you think of it as a translation followed by a oriented rotation, so I can draw something like this. So I'll let me draw something like this. So I have something like this now. This is my so I think I should have written m. Yes, right. So this is m circle gamma of s. Okay, right. Now see, so what is the claim? The claim is that this m circle gamma of s that will also have a Frenet-Serret frame. Okay, and it will also have the Frenet-Serret relations. The first thing you have to notice is that m circle gamma s will also be unit speed parameterized. Okay, note that m circle gamma s, okay, will also be unit speed. And in fact, why is this true? So you see, it's just a matter of using this fact that we proved that m is a translation followed by an oriented an oriented generalized rotation, a member of the orthogonal group, special orthogonal group. Okay, member of the orthogonal group, determinant 1, which so by our earlier discussion, you see this m is nothing but first you apply a g, then you apply translation. Okay, so so let me say the following thing. I mean, this t is a translation and this g is an oriented linear isometry. okay, and so you know what this is. Basically, you see this, you know, if you want to, you know, if you want to fix this, uh, um, so this G is, you know, G is just m minus m0, okay, but then because m may not take 0 to 0, okay, the only thing that prevents an isometry from being linear, that it will not take 0 to 0. So G is m minus m0 and T is translation by m0, okay. So that is something that we have already done, okay. So there is this kind of a, you know, decomposition that we have already done. So I'll just write it here. G is m minus m of 0 and T is translation by m of 0, okay. And this is something we have already seen, right? And the important point is that, you know, G is oriented. So G is actually in I will just say the matrix of G will be in SON, SO3 in this case, okay, because it's n is 3 here, okay. So what will happen is that, you know, our so this new curve m circle gamma, if you write it, you see, so if you write this m, how will it be? It will be just, you know, m of any v will be you know, T m of 0 circle G of v, and so this will be just, you know, so what I want to say is so it will be, so let me write it like this. I'll just write it as G of v plus m of 0, okay. So I want to write it like this, okay, so that I can make some computations with this, okay. So first apply T circle G acting on V means first apply V to G, G to V, and then apply Tm0. So if you apply V to G, you will get GV. Then translate by M0 means you have to add M0, right? This is what it is. And of course, this is the same as saying G, if you take this M0 to the left side, it's the same as saying G is M minus M0, which is what I have written here, okay. Sometimes I'm forgetting to put the arrow on the 0, and sometimes I'm not, I am putting it, so don't get confused, okay. So anyway, the point is, look, so I want you to look at this new curve. So you see, you look at m circle gamma of S, look at this curve, okay, and let us calculate, so look at this curve. This is the, you know, this is the new curve that you have gotten, okay. First of all, calculate its tangent, what is the tangent vector. So T, so let me write this as T of m circle gamma of S, okay, is going to be just, you know, m circle gamma of S dot, okay. This dot is d by ds, so this is going to be just d by ds of m of gamma of S, okay. This is what it is, all right, by definition. And yeah, but what is m of gamma of S? Yeah, so you see, what is this? This is going to be d by ds. M of gamma of S, you just plug it here, you will get g of gamma of S, okay, plus m of 0. I will forget putting the arrow on the 0, okay. I will get this, but you see, this m of 0 is a constant vector, and d by ds is going to be 0. So what I will get is, I just get d by ds of g of gamma of S, okay. And mind you, G is a constant matrix. See, mind you, G is a what? G is a special orthogonal group element. So its entries are all constant real numbers, okay. And therefore, d by ds will go across this. So what will happen is that I will get G into gamma dot of S, okay. And but what is gamma dot of S? It is just T cap of gamma. So this is G T cap of gamma of S, okay. And so you see, T m circle gamma S is just G T cap gamma S, and but you see, T cap is what? Is a unit vector. because t cap gamma is a unit vector, because gamma is unit speed. So t cap gamma, by the way, remember that t cap gamma is just gamma dot. Okay, norm gamma dot is 1 because gamma is unit speed. Therefore, t cap gamma is just a unit vector. But what is G? G is it is an isometry, linear isometry. It will preserve lengths. Okay, so G of t cap is also unit vector. Okay, mind you, it's a linear isometry. A linear isometry will preserve dot product, it will preserve norms, it will preserve lengths, angles, everything. Okay, so G of t cap is also unit vector. Therefore, the moral of the story is that this calculation tells you that the T of M circle gamma S is actually a unit vector. Therefore, it is actually T cap of M circle gamma S, and because T is T cap, it means M circle gamma S itself is unit speed. Okay, so that's what you can infer from this. Okay, so this implies that a T M circle gamma S is equal to T cap M circle gamma of S, and hence and of course this is equal to G of T cap gamma of S, and hence M circle gamma of S. Okay, so this M circle gamma, all that at all places, it's better to put a bracket so that you understand it clearly. So let me do that. I'll put a bracket here, I'll put a bracket here. So, and hence M circle gamma of S is indeed a unit speed curve. Okay, because it's T equal to its T cap. Okay, and basically as you can expect, the idea is very simple. What am I getting? I am getting the T cap of M circle gamma to be G times T cap of gamma. All right, and you see T cap is the first member in the Frenet-Serret frame. So what you are saying is the first member in the Frenet-Serret frame for gamma is taken by G to the first member in the Frenet-Serret frame of M circle gamma, and now it will follow that the same things will happen for the second and third members, namely the the principal normal and the binormal. Okay, so so let me write this. But before that, you see, what is it that we are trying to do? We are trying to show that this new curve M circle gamma, which we have just now verified is also unit speed curve. We are trying to show it has the same curvature and torsion functions as the original curve gamma itself. So let's first calculate the curvature. You see, K of or kappa of oops. So kappa of M circle gamma of S, what is this? What is the definition of the curvature function? So it is the magnitude of the acceleration, and the acceleration is second derivative of the the displacement. Okay, so it's gamma double dot. In this case it will be M circle gamma double dot. So this is just going to be norm of M circle gamma of S, and mind you, I will put a double dot on top of. Okay, and what is that? This is the definition of the acceleration, the curvature. All right, which is the magnitude of the acceleration. So and mind you, double dot means what? Is d squared by ds squared. Dot is d by ds, double dot is d squared by ds squared. So I will get norm d squared by ds squared of M circle gamma of S. Okay, and but then you see, now again keep using this formula that M circle gamma S is G gamma S plus M0. So this will become d by ds d by ds, M of gamma of S is just G gamma S plus M0. Okay, and this is going to lead to d by ds of G circle gamma S. Okay, and this is something that we have already I have already written down. So it is just going to be the G will come out. I will get G d by ds of gamma S is going to give me gamma dot S. Okay, and d by ds of this M0 is going to go away because M0 is a constant vector. All right, so I'm going to get this. Okay, and then if I do one more d by ds, G is always, G is a constant matrix, it will keep coming out. So what will happen is that I will get I mean constant matrix, when I say constant matrix, I am thinking of G as a matrix acting on a column vector, which is the same as the linear map defined by the matrix that represents G. Okay, so there is always this, there is always going to be this abuse of notation, that when you look at a map, when you look at linear isometry, you, if necessary, think of it as a matrix, and the linear map it defines. Okay, or you think of it just as a function abstractly. Okay, and we will interchange these notions because we already understand that language. Okay, so this G will come out, so I will get G d by ds of gamma dot of S. Okay, and mind you, I am able to do this just because G is a constant matrix. Okay, and this is going to be norm G gamma double dot of S. Okay, but you see, now again look at this, G is a linear isometry, so it will preserve norms. So norm G gamma double dot S is the same as norm gamma double dot S. Since G is a linear isometry and hence preserves norms. Okay. In fact, G is a linear isometry, it preserves even dot products, and preserves dot products means it will preserve norms. Okay, so that's the G disappears. But what is this? What is norm gamma double dot S? It's just the curvature function of gamma. So this is just kappa gamma of S. So you see, the curvature function of the new curve is the same as the curvature function of the old curve. So the curvature functions are the same. Okay, then so this is a key step in before you go ahead and try to show that the torsions are the same. To show the torsions are the same, what you will have to do is you have to use the definition of torsion, which is essentially the third Frenet-Serret relation. But the definition of torsion involves the binormal. So you have to compute the binormal. But the binormal is what? The binormal is the unit tangent cross the principal normal. So therefore you have to first compute the principal normal. But computing the principal normal will involve using the curvature, because that's how the principal normal is defined from the first Frenet-Serret equation. So that is the reason why I first computed the curvature. So now what we can do is go ahead and show that the principal normal of the moved curve, okay, is it is just G applied to the principal normal of the original curve. We already proved that the tangent for the moved curve is G applied to the tangent of the original curve. Now I am going to do it for the second member, which is the principal normal. So you see, calculate n cap of M circle gamma of S. What is this? This is by, that's because if you want, you can write it and see. Suppose I write a constant, I write a constant matrix. So okay. So if it helps, you can think like this. See, as an aside, let me write somewhere here. You see, if I have a matrix, let us say, let me put A11, A12, A13, A21, A22, A23, A31, A32, A33. It's a constant. These are all constants. And then suppose I put some f of s, g of s, h of s. Okay, and I do d by ds. You will see that this is what will be the if you compute the matrix derivative, if you first compute the matrix product, then it will be first row into first column. I will get A11 fs plus A12 gs plus A13 hs, right? And then if I apply d by ds, the d by ds will pass through the aij's. Okay, therefore you can see that this is the same as A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, and you can put the d by ds on this side. I mean, the point is the aij are all constants. So the d by the derivation, when you differentiate, a constant can be pulled out, right? So that is the reason why the g comes out of the derivative here and here. Okay, that's quite clear, right? Okay, so so you see, so let's go ahead and look at what is the principal normal for the moved curve. What is the definition? The principal normal is always defined by the first Frenet-Serret. It is the t cap of the curve divided by the curvature. So this is going to be t cap of the moved curve divided by the curvature of the moved curve. Okay, but you see, but what is the t cap of the moved curve? So I should write t cap dot. So I have to be careful. I think I wrote the dot there. Did I do that? Yeah, you have to be careful with these dots here, yeah. So when you define the normal here, that is the t cap dot there. That's very, very important. That is the first Frenet-Serret equation. So so I have to take so this n cap for the moved curve is take the t cap of the moved curve and put a dot on that, okay, and then divide by the curvature. But you see, remember, this step necessitates that for the moved curve the curvature should never vanish. Okay, but that is all right, because you see the original curve curvature and the moved curve curvature are the same, we have proved, and we have assumed that the original curve curvature never vanishes, which is necessary for the torsion for the original curve to be defined. So this never so in fact it's actually always positive, so I'll just write it as positive. Okay, this implies that this guy, this is positive, okay, by by this by this equality. Okay, therefore this fellow, the curvature of the new curve is positive, therefore you can divide, okay, and it makes sense because of the curvature of the moved curve is positive, therefore the torsion for the new curve is well defined, okay, and therefore you have this all this makes sense. So you have to justify that the new curve is first unit speed, the moved curve is also unit speed, then you justify that the the curvature of the moved curve is the same as the curvature of the original curve, and therefore it is always positive, and therefore for the new curve also the torsion is defined, and then once the torsion is defined, there the Frenet-Serret frame is defined for the new curve, and the Frenet-Serret relations also hold for the new curve. You have all that and you can use all that, okay. So that's what I'm using. So what I'm here using is the first Frenet-Serret relation for the new curve, which is the moved curve, okay. And but what is t cap? It is d by ds, so it is going to be 1 by, so what I will do is I'll replace this k curvature of the new curve by the curvature of the old curve, so I will just write it as 1 by k k gamma of s, okay. I'll put this, and what is the fellow on the numerator? The fellow on the numerator is d by ds of t cap m circle gamma of s, okay. This is what it is, okay. But you see this t cap, look at this equation, the t cap of the moved curve is g applied to the t cap of the original curve. That's what we have proved. So plug that in here and you're done. So you will get d by ds of g applied to the t cap of the old curve, okay, by k gamma of the old curve, okay, k gamma of s, which is the curvature of the old curve, okay. And again, g is a constant, it will come out. So what you will get is once this g comes out, you will get d by ds of t cap, and that is t cap dot. So you will get t cap dot gamma of s divided by k gamma of s. But this is by the Frenet-Serret for the first Frenet-Serret equation of the original curve, the first curve gamma. This is exactly the principal normal of the first curve. So this is equal to n cap gamma of s. Therefore, you see, and sorry, there's a g out here. Okay, so there's a g out. So the g will come out. Okay. So therefore, the moral of the story is, you see, the n cap, the principal normal of m circle gamma of s is just g applied to n cap of gamma of s. Okay. All right. Now, what do I have to show? I will show next that the binormal goes to the binormal, okay. But then the point is that to show that you know, binormal goes to the binormal, probably there are two ways of doing it. Yeah. So, okay. So there are two ways of seeing this, but let me explain both of them. So you see what is so. Therefore, what have you got up to this point? T cap of the new curve is G applied to T cap of the original curve. N cap of the new curve is just G applied to N cap of the original curve. Okay, that we have already got. What we want to show is the same happens to the third one, which is basically the binormal. Okay, but so how do you do this? You calculate B hat of M circle gamma of S. What is B hat? B hat is supposed to be the third vector, unit vector that completes the right-handed triad. So it will be just T cap cross N cap. So it will be T cap M circle gamma cross of S cross N cap of M circle gamma of S. Okay, but you see for T cap and N cap we have already got these expressions. So it will be G applied to T cap gamma, okay, cross G applied to N cap gamma. Okay, this is what it is. Now mind you, this G as a matrix, this matrix is what? It is in this is in SO3. Okay, determinant of G is 1 plus 1. It's oriented. Okay, now what I want you to understand is that you see you know that the orthogonal the elements of the orthogonal group, which are the same as linear isometries, okay, they will preserve dot products. Okay, so if they preserve dot products, what will happen? They will preserve magnitudes of angles, they will preserve lengths, they will preserve norms. Okay, the only thing that they will mess up is orientation. Okay, and orientation has got to do with the cross product. Okay, so if you really look at it, this will be the same as determinant G. So I want to say the following thing: determinant G times G of T cap T gamma cap cross N gamma cap. Okay, and therefore determinant G is plus 1. All right, so it will be plus 1 times but T cap cross N cap is B cap. Okay, so you'll get G B cap gamma. So therefore you will get B cap M. So I forgotten to put an S everywhere. Okay, now let me just tell you something to make things more clear. You see, look at this picture. So you suppose I have a vector V. Okay, this is the origin. I have this vector V, and then let's draw a picture. Okay, then let's suppose I put a vector W. Okay, now these V and W, they are lying on a plane. Okay, and what is V cross W? This V cross W, the cross product is the magnitude of the cross product is going to be norm of V cross W, and the unit vector in the direction of V cross W will be this V cross W cap. What is this V cross W cap? So you are supposed to take the unit vector perpendicular to the plane of V and W, and in such a way that as you move from V to W, okay, the right hand rule, the thumb rule points towards the unit vector. Okay, so in this case, in my picture, what will happen is that if I go from V to W like this, okay, then it will actually go down. My V cross W cap is going to be here. Okay, it will be like this, the way I have drawn it, because as I go from V to W, I have to go clockwise. Okay. Okay. Now, but just think about it. Suppose I apply G to this. What is going to happen? See, G. What does G do? It preserves lengths. It preserves norms. It preserves angles. So what is going to happen is I am going to see G will. I will get some other plane. Okay. And mind you, G is a linear map. It takes 0 to 0. So it will map a plane back to a plane. A plane passing through the origin, when you apply G, it will go to another plane. And that the original plane contained V and W. So the new plane will contain 0 and GV and GW. So in the new plane, you will get something like this. Here is your 0 again in the new plane. So if I call this plane as pi, this will be G pi. This is the image of G. That's a plane passing through the origin. This will contain this, there will be this GV here, G of V. Okay. And then I will have G of W here. And what you should notice is that, G preserves norms. So you see, norm GV will be the same as norm V, and norm GW will be the same as norm W. Okay, since G preserves norms. Okay, and what does G also do? Mind you, it's a linear isometry, so it preserves dot products. Therefore, it even preserves angles. Okay, mind you, it's an isometry. It will preserve angles. Magnitudes of angles will be preserved. Only the sense may get messed up. So what will happen is that if this angle from V to W is theta, okay, then the angle from GV to GW, okay, this angle will also be the same theta. Okay, but let me not worry about let me worry only about the magnitude of the angle and not the direction. Okay, because the direction part is going to be taken care of by the unit vector. Okay, so what will happen is, now look at this. What is going to be GV cross GW? What is going to be this new vector? See, this new vector is going to be, by the definition, norm of this into the unit vector along that direction. So it will be norm of GV across GW, okay, into GV cross GW whole cap, okay, by definition. All right, but what is norm GV cross GW? This is going to be just the same as norm V cross W, because norm GV cross GW is what? It's norm, this quantity is going to be, if you take only this quantity is going to be norm GV, norm GW into mod sin theta. This is what it is, right? But this is the same as norm V, norm W sin theta, mod sin theta, and that is, you see, just the norm of V cross W. Okay, so basically what this G does, if you take, it preserves dot products. For cross products, what it will do is it will preserve norms anyway. The only thing is it will mess up the orientation. Okay, so this if you look at it, if you look at this picture, you see this this unit vector that I have drawn here, this unit vector, this guy here, this is orthogonal to both V and W. Okay, but you see the G is orthogonal transformation. It will preserve perpendicularity. So what is going to happen is that, you see, if you this G of V cross W cap, okay, G of V cross W cap will be a unit vector, and it will be perpendicular to both GV cap and GW cap. Okay, all right. Therefore, what does this tell you? It only tells you that G of V cross W cap has to be plus or minus GV cross GW whole cap, and it will be plus because G is going to preserve the orientation, because G is an orientation preserving map. Okay, so so let me let me write this: V W V cross W cap, okay, right-handed, oriented. So let me just put it as oriented. Okay, right-handed, and this will imply that GV GW G of V cross W cap will also be oriented and right-handed. Okay, and remember that this V cross W cap is orthogonal to both V and W. So G of V cross W cap will also be orthogonal to GV and GW. Therefore, but you see the unit vector perpendicular to both GV and GW is GV cross GW cap with a plus or minus. So therefore, what this, all this will tell you is that G of V cross W cap, mind you, G of a cap vector will also be a cap vector. G of a unit vector will be a unit vector because again G is an isometry. Okay, so G of V cross W cap is going to be a unit vector. It's going to be perpendicular to GV. It's going to be perpendicular to GW. So it has to be just GV cross GW cap plus or with a plus or minus sign. So this has to be equal to plus or minus GV cross GW whole cap. Okay, and in fact equal to plus GV cross GW the whole cap. Okay, so basically I'm just saying, I mean, all this is just to convince you that if G is a orientation preserving linear isometry, okay, what it will do is it will simply preserve the cross product. Okay, that's all I'm trying to say. Okay, and so the moral of the story is that's what I have used here. I wrote this determinant G explicitly here to emphasize that there's a plus 1 and not a minus 1. So you see, G T cap cross G N cap will be G of T cap cross N cap. Okay, because G is a orientation preserving linear isometry. Okay, that's what I have done. All right, and therefore this finishes the proof that you see the third member, namely not only the unit tangent and the principal normal, the binormal, all the three are moved by G from that of the old curve to the new curve. So you have got that. Okay, now there's only one more thing I will tell you, that the torsion of the new curve is the same as the torsion of the old curve, and for that again I will use the third Frenet-Serret relation, which gives you what the torsion is. Okay, so therefore thus G takes gamma to M circle gamma. Okay, it takes the Frenet-Serret frame of gamma, which is T cap gamma, N cap gamma, B cap gamma. They respectively go to G T cap gamma, which is T cap of M gamma, M circle gamma. This goes to G N cap gamma, which is N cap of M circle gamma, and this goes to G B cap of gamma, which is B cap of M circle gamma. Okay, and it will take K gamma to K M circle gamma. Okay, I mean they are equal actually. Okay, and the claim is that if you try to calculate tau gamma, that will also be equal to tau of M circle gamma. So that is the claim. That is the only thing that is left. So basically that will prove that the new curve and the old curve have the same curvature and torsion functions. Okay, so how do you do this? You see, what is a torsion of the M circle gamma, the new curve of S? You see, what is the third Frenet-Serret relation? You have B cap dot of M circle gamma of S is equal to minus tau M circle gamma of S into N cap M circle gamma of S. Okay, this is the third Frenet-Serret relation. Okay, so if I just write it out, so let me write this out. Frenet-Serret for M circle gamma will be, you will normally write T cap dot N cap dot B cap dot is equal to the Frenet-Serret matrix, which is 0 kappa 0 minus kappa 0 tau 0 minus tau 0, and here you will put T cap N cap B cap. Okay, and therefore B cap is going to be last row into this, so I will get B so b cap dot will be minus tau times n cap, which is what I have written here. Okay. So therefore, from this, what is how do you get tau? You just take dot with the n cap dot on both sides. So therefore, tau is minus b cap dot m circle gamma of s dot n cap dot of m circle gamma of s. Okay, this is what it is. But you see, what is this? This is minus d dot is d by ds. So it's d by ds b cap of m circle gamma of s. Okay, this dot. The other fellow is going to be n cap of m circle gamma of s. Okay, and so let me continue here. So I will get, but you see, b hat m circle gamma is g b of gamma, so use that, and n hat m circle gamma is again g of n of gamma. So this will be minus d by ds g b cap gamma s, okay, circ dot g n cap gamma of s. Okay. Okay. Now again, g is a constant matrix, it will come out of the derivative. So I will get minus g d by ds of b cap gamma s, okay, dot g n cap gamma of s. Okay. But now watch, g is a linear isometry, so it preserves dot products. So gv dot gw is just simply v dot w, so g disappears. So this just becomes minus d by ds b cap gamma s dot n cap gamma of s. Okay, since g linear isometry implies g preserves dot products. Okay, therefore the g disappears. And what is this? This is just b, so this is going to be minus b cap dot gamma s dot n cap gamma of s, and that is that is just the torsion for gamma of s by definition. Okay, and therefore on the left side we started with the torsion for m circle gamma, therefore you get torsion of m circle gamma of s is equal to torsion of gamma of s. So that's it. Okay. So what you have proved is, if you start with the curve, unit speed curve, and move it by a rigid motion, the new curve continues to have the same curvature and torsion. All right. Now what more we have to prove is, we have to show two more things. We have to show if two curves, okay, are such that they have the same curvature and torsion, then one can be moved to the other by a rigid isometry. So we have to construct a rigid isometry. Okay, all right, and you also need to say that yeah, so what this will involve is some insight from the theory of first order differential equations. Okay, and so you see why the theory of first order differential equations comes in, especially the existence and the uniqueness of solutions to first order differential equations. Why that comes in is because you see the Frenet-Serret relations are themselves a system of differential equations. They are first order linear differential equations, and the curve itself is thought of as a solution. It is the evolution of that first order differential equation. It's a solution for that equation. Okay, and therefore, and first order differential equations, linear differential equations are the easiest to solve. Okay, and normally in one variable you use an integrating factor. All right, and you also know that in general, if you have a differential equation of order n, okay, if it is linear, it will involve n arbitrary constants. So since this is a first order equation, it will have only one constant. Okay, and these constants in a solution of a differential equation, they are determined by the initial or boundary conditions. Okay, so basically in this case it's just first order, there's only one constant, and that one constant is for example giving a point through which the curve passes and a frame there which should match with the Frenet-Serret frame. Okay, so basically we'll use the fact that if you try to solve the Frenet-Serret differential equations for a curve, you will get a one parameter family of curves. But if you want to fix the curve, you have to fix a point through which the curve passes, and at that point you have to give me one particular Frenet-Serret frame. If you do that, then the curve is fixed. Okay, so we have to use that. So if you use that, okay, you can also show that if two curves have the same curvature and torsion functions, there is really a rigid isometry that moves this to that. And once we do that, what we have established is that we have proved that there is a one-to-one correspondence between rigid isometry classes of space curves on the one hand and curvature and torsion functions on the other hand. Okay, so that is your classification theorem. So this is the mathematical, this is the amount of mathematical work that is involved in trying to say this, make this statement precise, that curve is controlled by its curvature and torsion. Okay, so this is all the mathematics that is involved. Okay, so we will do that in the next lecture. Okay, so I'll stop here.